So I very briefly, in the last lecture, got into the next big project, which is ultimately the quantization of the electromagnetic field. So let me go over some of the motivation for the steps that we'll be taking tonight and in the following lecture. Up to this point in this course, we've mainly been using the electrostatic model when it comes to the interaction between charged particles and the electromagnetic field. In the electrostatic model, if you have some collection of charged particles, let's call them Q1, Q2, and so on, collection of particles, and you choose a field point, let's call it X, and let's call the positions of the particles R1 and R2. So the R's give the positions of the particles, and the X is the field point. If you go to this field point, and if you're working in the electrostatic model, you measure an electric field there, E is a function of position X. That electric field is determined by the charges and by their positions just by using Coulomb's law. Each particle produces an electric field vector, pointing towards the field point, and you add them up and you get the total electric field. So in a quantum mechanical description of the charged particles, this is just I'm not writing down the formula, but it's just Coulomb's law that I'm talking about here. So if you write down the quantum mechanical or Hamiltonian or wave function for the charged particles, you can see that the electric field, being a function of the positions of the charged particles, becomes itself an operator which just depends on the charged particle positions. In other words, it might as well be a matter operator. It's something that depends only on the matter degrees of freedom and is not an independent dynamical variable. Now, on the other hand, we know the electrostatic model is only an approximation because Coulomb's law, at least in the version I'm thinking of it here, is not retarded. So there's no retardation. That's certainly one approximation because it takes time for light signals to travel from the particles to the field point. Moreover, real electromagnetic fields exhibit phenomena such as radiation, electromagnetic waves, and so on, which are not encompassed by the electrostatic model. So in order to incorporate those kinds of phenomena, especially emission and absorption of radiation, into a quantum mechanical description, it's going to be necessary to go beyond the electrostatic model to treat the electromagnetic field as a dynamical system in its own right, which is coupled to the matter degrees of freedom. So this means we're going to move to a new and more realistic description of the interaction between matter and an electromagnetic field, which will consist of two parts. There will first of all be a matter part, which is described more or less the way we've been doing it so far in this course. Then there'll be a field part, by which I mean the electromagnetic field. And these have separate classes of degrees of freedom, which will be interacting with one another. Now, of course, what we've been doing in this course so far is treating the matter by means of quantum mechanics. We've been doing a lot of that. As far as the electromagnetic field is concerned, we could, if you think about it, you might consider treating it either by classical mechanics or by quantum mechanics. Let's just look at the possibilities. One possibility is to treat the electromagnetic field classically. That would mean using just the standard Maxwell's equations and the type of stuff you find in Jackson's book for describing the field. However, if we want to couple a quantum matter to a classical electromagnetic field, we obviously have a kind of hybrid system in which some degrees of freedom are classical and some are quantum. These hybrid degrees of freedom, in this case, if you can do that, and people do it, it's called the semi-classical theory of radiation. And it's quite useful, for example, in quantum optics, and it's used a lot. It is, however, from a fundamental standpoint, not very attractive. Let's just say that trying to make a hybrid system like this wreaks havoc with the measurement postulates of quantum mechanics, and if you push its interpretation very far, you run into a lot of difficulties. I'll just mention that this notion of having hybrid classical quantum systems is not restricted to this type of system, but it's actually of current interest because of phenomena such as Hawking radiation. Hawking radiation is a prediction of a theory which is based on a hybrid classical quantum system. In that case, the quantum part is the electromagnetic field or other quantum fields, and the classical part is the gravitational field. People couple the quantum fields with the classical gravitational field because they don't know how to quantize the gravitational field. That's the reason for doing it. In any case, there's been some notable developments in using models like that. Anyway, that's quite a tangent from where we want to go. What I want to say tonight is that it's preferable to use a quantum description of the electromagnetic field so that when we combine the matter with the field, we have a fully quantum system. We know what that's going to involve, tensor products of Ket spaces and things of that sort. That's where we're aiming to make a start on this tonight, and the next lecture will continue with it. However, to carry this out, what we need, therefore, is a quantum description of the electromagnetic field, assuming we know the classical description, because we all took Physics 209 last semester, and 110 AB before that. The problem then is how to go from something we know, which is the classical description, over to the quantum description of the electromagnetic field. Now, that raises a general question, which is quite a profound and deep one, about which a lot can be said, which is how do you pass from a description of a dynamical system, which is a classical description of a dynamical system, to a corresponding quantum description? And the first thing to say about that is that there can be no deductive way of doing this. You can't set down any rigorous rules that will do that, simply because there's more physics in quantum mechanics than there is in classical mechanics. There's all kinds of surprises that are typically waiting for you in a real application like this. It's true that in the current mathematical world, they have what they call geometric quantization, which in design is intended to be a method of passing from something like a classical system to something like a quantum system, using methods that are mathematically compelling. I think it's the best way of saying it, mathematically natural. And that program has been quite successful for certain areas of mathematics, such as representation theory, over the last 30, 40 years or so. It's quite an important subject, but it's not what we're talking about here, because here we're doing physics and not mathematics. All right. In any case, if you had to put down rules for how to go from classical mechanics to quantum mechanics, for some system, if you knew a classical description, one of the ways of laying them out, or at least giving an outline, would be to write down what works for mechanical systems. And if we do that, it would run something like this. For a mechanical system, you could say, let's start with the equations of motion. So a mechanical system, they'd be Q double dots is equal to some, it's basically F equals ma here, it's accelerations, is given by some forces on the right-hand side. So this is the classical equations of motion. We'd start here. And then what you'd do is you'd extract from the classical equations of motion a Lagrangian, which is a function of the q's and the q dots. By the way, the q's here are what you call the generalized coordinates of the system. There's a question of saying what those are. In a mechanical system, they would be the positions of the particles. But in any case, you go over to Lagrangian, which by using the Euler Lagrange equations reproduces the equations of motion. And then from there, you go over to the classical Hamiltonian, H or Q and P by the standard prescriptions which are used in classical mechanics books. And then from the classical Hamiltonian, you can pass to quantum mechanics by reinterpreting the Q's and P's as operators. I'll indicate that by putting hats on them. For example, the Q hat can be seen as multiplication by Q. When we write it out, Q hat goes over into multiplication by Q, and the P hat goes over into minus IH bar dDQ. This is a representation of the canonical commutation relations, or the Heisenberg-Born commutation relations, in terms of operators. This is a simple method of quantization. Once you have a classical Hamiltonian, it comes under the name of Dirac, or sometimes called canonical quantization. And it is the simplest one that there is. It's inadequate for more sophisticated problems, but it'll work for what we want to do. And this is roughly the outline that we're going to follow in passing from classical to quantum mechanics for the electromagnetic field. That's the goal of the next couple of lectures. Actually, for tonight, mainly what we're going to be doing is analyzing the classical Hamiltonian to the point of getting, the classical mechanics to the point of getting the classical Hamiltonian. We're going to do this from Maxwell's equations. Now, I'm not going to go through the Lagrangian. Instead, I'm going to take an abbreviated route that involves going straight from the equations of motion to the Hamiltonian by using some guesses. And I'm going to do that because it's simpler, and the Lagrangian involves too many technical details that don't really contribute much to our understanding. All right, so that's an outline of where we want to go. So let's start with the equations of motion then. These are Maxwell's equations. So let me organize them in the following way. Let's put down first the homogeneous Maxwell equations. Del dot B equals 0, and del cross E, Faraday's law, minus 1 over C dV dt. I'm using Gaussian units. These are the homogeneous equations of the Maxwell equations. And And then we have the inhomogeneous ones. There's the divergence of E is equal to 4 pi rho. And the curl of magnetic field B is equal to 4 pi over C times the current J plus 1 over C dE dt. These are vacuum Maxwell equations. And these are the inhomogeneous equations. They're inhomogeneous because they contain the driving terms, which are the current, which is the charge density and the currents, the matter that's driving the electromagnetic fields. Rho and J, of course, for consistency of Maxwell's equations, have to satisfy the continuity equation. Otherwise, there's no solution to Maxwell's equation, so we assume that. All right, so these are the equations of motion. Now then, the homogeneous Maxwell equations, as you all know, imply the existence of scalar and vector potentials, the phi and the A, such that the electric and magnetic fields are given in terms of the potentials. E is minus grad phi, minus 1 over C dA dt, and the B is equal to del cross A. And so those are interesting substitutions to use. The potentials, expressing E and B in terms of the potentials, causes the homogeneous equations to be satisfied as identities. And so if we turn just to the inhomogeneous equations, that's what's left. If I plug these things in and just work it out over here, the Gauss's law becomes the minus del squared phi minus 1 over C partial respect to T of del dot A is equal to 4 pi rho. Allow me to change signs on that to put it into a kind of standard form that I want. If we plug in the B equals curl A into Ampere's law, it becomes del cross A becomes, we put it somewhere down over here, it becomes del of del dot A minus del squared A is equal to 4 pi over C times the current J, and then we have plus 1 over C dT of the electric field, which is, this would be with a minus sign, minus gradient phi, minus 1 over C squared, B squared A dt squared. So let me rearrange that into a nicer form to write over here to summarize. So let me change the signs again, minus here, plus there, minus there, plus, plus. Then we get del squared A minus 1 over C squared D squared A dt squared, which is obviously a del inversion or wave operator acting with the vector potential, takes care of that term and that one, bringing that one across. Then we have minus the divergence of del dot A, and that's equal to, on the right-hand side, minus 4 pi over Cj, minus or plus 1 over C dt, the gradient of phi. Okay, and having done that, we now have the equations of motion in terms of potentials. Let me take this out, I don't need that anymore. So these are the equations of motion in terms of potentials using an arbitrary gauge. I'll come to the point about gauge invariance in just a minute. One of the lessons of the equations of motion in this form is that as you can see, the equations for the vector potential are second order in time. And this reminds us of the accelerations which appear in Newton's laws. And it suggests that the Q's of the electromagnetic field are tied up with the vector potential. This turns out to be true. But these are, in effect, the Q's of the field. So in fitting this pattern of classical Hamiltonian mechanics, that's going to be something to keep in mind. On the other hand, compared to a classical dynamical system, there are some new issues which arise here. One of them is the non-uniqueness of the potentials. As you no doubt know, if you replace the potentials, let's say A by a new potential A prime, which is given by A plus the gradient of a scalar, which I'll call chi, and then phi goes into phi prime, which is phi minus 1 over C d chi dt. Chi here I'll call the gauge scalar. It's the scalar that specifies the gauge transformation. Then, as you know, the new potentials A prime and phi prime give you the same E and B as do the old ones. So this means that potentials, scalar and vector, for given electric and magnetic fields are not unique, but can be changed by this gauge transformation into something else. An interpretation of this is to say that potentials A and phi contain a physical part because the physically measurable electric and magnetic fields can be computed from them. But they also contain a non-physical part because that's the part that's changed when you do a gauge transformation. So by working with A and phi, the potentials, as the descriptors of the degrees of freedom of the electromagnetic field, there is contained in there a non-physical degree of freedom connected with gauge invariance, gauge transformations, partly physical, partly non-physical. So one of the issues that we have to face in the quantization of the field is to somehow eliminate or take care of the non-physical degrees of freedom. The simplest way to do it, and on a first pass, this is the way to do it, is to choose a gauge. And so what choosing a gauge does is it in effect pins down, by convention, the non-physical part of the potentials, leaving behind only the physical part. Now the gauge that we're going to use is Coulomb gauge, which is the best for an introductory course like this. Coulomb gauge, by definition, is one in which the divergence of the vector potential is equal to 0. Now, you can show, this should appear in books on electromagnetism. I don't know if Jackson does it, but it's a simple demonstration. You can show that if you have, for given E and B, if you found some phi and A, which are potentials that satisfy these equations, it may not be true that L dot A is equal to 0. But the statement is you can always find a gauge scalar chi such that after doing a gauge transformation, the new A prime does satisfy the Coulomb gauge condition. And so the result of this little calculation, little theorem, is that there's no loss of generality in using Coulomb gauge, or one might say Coulomb gauge always exists. So going forward, we're going to assume that we're using Coulomb gauge, that delta A equals 0. If we do this, and you can see the equations of motion simplify, so I'll use my eraser to do that. This term goes away right there, and this term goes away there in the Ampere's law. And so what you've got is you see, it's Gauss's law, a version of Gauss's law at the top, and a version of Ampere's law at the bottom. And now, right away, there's some things that appear here in these equations. Some conclusion can be drawn right away, which partly explain why this is called Coulomb gauge. If we look at the plus, you see the first equation for phi, the equation for the scalar potential, is really the Poisson equation, which is, of course, familiar from electrostatics. But it's a little bit tricky because we're not doing electrostatics, we're doing fully electromagnetism with all the full time dependence. There's nothing in here we made any assumptions or approximations. The solution of the Poisson equation is given in all generality by using the Green's function for the Laplacian operator. And the solution is unique if we assume that phi goes to 0 at spatial infinity. Under that assumption, then the solution that we get from the Poisson equation is that phi of x and t is the integral over all space d cubed x prime of the charge density rho evaluated at x prime in t divided by the Coulomb denominator x minus x prime. This is the unique solution of the Poisson equation. And now, the main point to make about this is that this isn't quite electrostatics because we're allowing the charge density to be a function of time. And moreover, notice that the scalar potential which results here is determined by the charges at other places in the scalar potential at a position x at a given time t is determined by all the charges in the rest of the universe. That's what this x prime integral is, evaluated at their locations at the same time as the time at which we're measuring phi. In other words, this solution of the Poisson equation does not involve any retardation. Now, we know that there really is retardation. We know that signals cannot travel faster than the speed of light. So it would appear that all we have to do is go and measure phi, and we violated relativistic causality by using these formulas here. And so what's wrong? Well, what's wrong is you can't measure phi, because phi itself is not physical. What's physical is the electric field. You can measure that. But that involves the grad phi and the vector potential term as well. And when you go through some analysis, you will find that the electric field is actually properly retarded and does not violate relativistic causality. So you might say that this non-retardation in the scalar potential is a mathematical artifact of the Coulomb gauge. And that's actually true. Nevertheless, it's useful to do it for the kinds of applications we'll be considering, because, in fact, a formula like this, it lies at the basis of the electrostatic approximation, which we've been using for much of the course so far. So understanding electrostatic approximation is tied up in understanding this formula. I'll come back to that later on, after making a digression into certain other topics. But in any case, this is one reason why this is called Coulomb gauge.